Hello, and welcome back to the course on classical electromagnetism. This is now the last lesson for chapter 6. So before we proceed with the lesson, let us first review some concepts. So these are the electrodynamics equation before Maxwell. So you have Gauss law, the divergence of an electric field is rho over epsilon naught. This is basically Gauss law for magnetism. And you have Faraday's law, the curl of the electric field is equal to the negative change in magnetic field with respect to time, and the curl of the magnetic field is proportional to the volume current density. So in this last lesson, we will discuss how Maxwell corrected all of the electrodynamic equations by introducing the concept of the displacement current. So Maxwell made a correction to Ampere's law. So if you will recall from our one of the equations in our discussion on magnetostatics, we have this continuity equation wherein the divergence of the volume current density must equal the negative time rate of change of the volume charge density. So this is the continuity equation. From volume charge density, when it moves, it now becomes a volume current density. So from Gauss law, rho, the volume charge density is just the divergence of E times epsilon naught. So we can write it like this. Now, if you go back to, the term here, epsilon naught, partial of E with respect to T, is what we call the displacement current density. So it's a fictitious current that is usually associated with a capacitor. It's basically the current that flows in between the plates of a capacitor. But take note, current doesn't actually flow. That's why there's the word fictitious, because it's not an actual current, but it is equivalent to the current. So you may be wondering why, if you have a capacitor, for instance, how does current flow through a capacitor? So there's a conduction current I, and when it leaves the capacitor, there's also a current I. But note that there's a gap here. That's not a conductor in between there. So what actually happens is there's a displacement current there. But that is actually not entirely a physical quantity. It's a theoretical concept to correct Ampere's law. Now, this will actually correct Ampere's law. So this is Ampere's law. If you take the divergence of Ampere's law, so the divergence of the curl of B, which is just the divergence of J, that's actually zero, because this is a law for the divergence of a curl is always zero. So what Maxwell did is he added a term, this term, mu naught epsilon naught, where epsilon naught partial of E with respect to T is just the displacement current density, mu naught JD. Basically, this is JD. So this term here is epsilon naught, mu naught is JD. So mu naught J plus mu naught JD, the displacement current density, such that if you take the divergence of this new general Ampere's law, you will actually get the value of 0, because del dot J, divergence of J, will give you this one, and then you will have a positive version of that one when you take the divergence of this, and it will result to 0. So theoretically, you didn't do something wrong here. So he added this term here to correct Ampere's law, and this is not the general Ampere's law. It now contains the displacement current. So in integral form, it's b dot TL mu naught I enclosed, but there is now an extra term, and this extra term is ID enclosed, or the displacement current enclosed. ID enclosed, or the displacement current enclosed. So the total current enclosed is now the conduction current enclosed plus the displacement current enclosed. So these are now Maxwell's equations. So even though these are not named after Maxwell's, the collection of all these four equations are called Maxwell's equation. So you have the Gauss law, and then usually they don't call this second law with any name, but can actually call this the Gauss law for magnetism. You have Faraday's law, and you have the general Ampere's law. If you have matter or dielectrics, then you need to shift to electric displacement and auxiliary field H, where the electric field and electric displacement is just related by the general permittivity, and the magnetic field and the auxiliary field is just related by the general permeability mu. So this is now Gauss law. This is the Gauss law for magnetism. This is Faraday's law in dielectrics, and this is Ampere's law in dielectrics. So you have a free current density, and basically this is actually displacement current density. Now, what if magnetic charges exist? What will happen to Maxwell's equations? So it's actually pretty interesting. It's very beautiful in a sense that you can really see the symmetry between electricity and magnetism, between electric field and magnetic field, if magnetic charges exist. A single north pole or a single south magnetic pole exists. So in that case, Maxwell's equation will look like this. So the only term added are these two terms. So instead of 0 for the divergence of the magnetic field, since it's no longer always a dipole, there's now a magnetic monopole, then you will now have mu naught through rho m. Rho m is the magnetic volume charge density. Rho is the electric charge density. So they are now symmetric. The divergence of E and the divergence of B are now totally symmetric. Similarly, for their curl, the curl of E and the curl of B is also symmetric. The curl of E is mu naught Jm, the magnetic current density, minus partial of B with respect to T, and then the curl of B is mu naught times the electric current density, and then you have partial of E with respect to T. So it's very symmetric. So Maxwell's equations actually begs for magnetic charges or magnetic monopoles to exist. And there's nothing wrong if magnetic monopoles actually exist, because you see the symmetry, and if you study nature actually loves symmetry. So but as far as experiments go, there's no evidence of magnetic charge density and magnetic current density. So basically, you go back to these terms being 0. So that one. Okay, let's have an example on displacement current. So a narrow gap in a wire, there's a very narrow gap in a wire, forms a parallel plate capacitor. So this is a very narrow, so one face of this wire, this cross-sectional area, has a surface charge density of positive sigma, and the other one is negative sigma. So essentially making a parallel plate capacitor. And current actually flows because this is a capacitor, so current will still actually flow. So there will be, even though there's a gap, but there's actually a current, a fictitious current flowing through the gap, and that is what we call the displacement current. Okay, so you're asked to find the magnetic field in the gap, a distance s, which is less than a, because a is the radius of the wire from the axis. So in this case, there's actually we make an Amperian loop. We make an Amperian loop, a circular Amperian loop in our gap. So in our Amperian loop has a radius s, and there will be the magnetic field here If this is the direction of the current, then the magnetic field direction in the loop is in that direction. And so the magnetic field and dl are both in the same direction. Okay. So the current density here is J. And in this region here and in this region here, there are no displacement currents. We assume that there are no displacement current. But there's a gap here. And for the charge or the current density to be continuous, there should be a current in this gap here, and that current or that current density is JD. So basically, the JD, the current in the gap here, the current density in the gap must just be equal to the current density J. So by the way, in the gap, there's only displacement current. There's no conduction current, and that is how the continuity of current flow basically works in a capacitor. So even though there's no actual current, but there's a displacement current basically taking the role of the conduction current in the gap, so that current will flow continuously in our circuit. So in this region here, you have conduction current density, but you don't have displacement current. But in this region here, you don't have conduction current, you only have displacement current. So JD is actually equal to J in this scenario. So meaning the displacement current density is just equal to J, assuming the current is in this direction, and assuming this direction is the Z hat direction, then you will just have the total current I over the total area, which is pi A squared Z hat. Okay. So in this case, our current density and displacement current density are all constant. They are constant. So we use Ampere's law, the integral form of Ampere's law. B dot dl is equal to mu naught I enclosed. Now, in our Amperian loop, in the gap, there is no I enclosed. I enclosed is 0, but there is displacement current enclosed, ID enclosed. Take note that in the general Ampere's law, the total current is the conduction current enclosed plus the displacement current enclosed. But in this case, there's no conduction current enclosed, only displacement current enclosed. How do we solve for the displacement current enclosed? Since we already know the displacement current density I over pi A squared, and this is actually constant. So since J is, which is equal to I over pi A squared, is constant, then this must also be equal to the this JD, displacement current enclosed over the area enclosed by our Amperian loop. So our Amperian loop is a circle with radius S, so its area is pi S squared. Therefore, cross multiply the displacement current enclosed is just equal to S squared over A squared I. You substitute that here, so B and DL are the same, and the magnitude of B is just the same at all points in the loop, meaning you can take it out of the integral and you have closed integral of dl is just the total length of our Amperian loop. The total length of our Amperian loop is just the circumference of the circle, which is 2 pi s. So we will have b times 2 pi s is equal to mu naught s squared over a squared I. So solve for b. We know that B is in the direction of phi hat, so B and DL are both in the phi hat direction. So we already knew the direction of B. We can now solve for its magnitude, and its magnitude is just equal to mu naught I s over 2 pi a squared, and its direction is phi hat. So this is now the magnetic field within the gap, and its direction is actually in the phi hat. So the current and the displacement current is in this direction along the Z hat direction. Therefore, the magnetic field is in the phi hat direction. It's curling around the displacement current. So that is how displacement current works. Okay. So another example. So in this example, you have a coaxial cable. So made of a solid cylinder, a very thin cylinder, and a cylindrical shell. So this is very common. You have a coaxial cable. So in your cable wires, that's a coaxial cable. So the current in the inner cable, the current moves in that direction, and in the outer cable or outer shell, the current moves in the opposite direction. But in this case, the current is alternating, meaning that is not the direction of the current always. That just half the time the direction is in that direction, but half the time it's in that direction. But at one time, the direction of these two currents are opposite of each other. Okay, so in this problem, you refer to this is actually another problem in the book. This is problem 7.16 in the book by Griffiths, Introduction to Electrodynamics by Griffiths, problem 7.16. And you are asked to find the electric field within the region, in this region, between the two cylinders, the cylinder and the cylindrical shell. And the electric field is actually this one. It's time dependent, and it's position and time dependent. It depends on S and it depends on T. So we will use this result. So in this problem, we are asked to find the displacement current density in the region between the cylinders. So for letter A, you're asked to find JD, displacement current density, and it's just epsilon naught partial of A with respect to T. So you just take the derivative of this with respect to time. There's only one term here that contains time, so sine omega t. The derivative of sine omega t is cosine omega t times omega. So there's an omega, so this will now become omega squared, and I naught cosine omega t is just I, and we will get values of mu naught epsilon naught I omega squared over 2 pi ln of B over S C hat. So this is now the displacement current density. Okay, find the displacement current. So to find the displacement current, if you know the volume current density, then volume current density is just current, displacement current per unit area. So therefore, displacement current is just integral of GD, displacement current density, times the area. So current per unit area times area, you get the displacement current. So we need to integrate this one. So you will have mu naught epsilon naught I omega squared. So since we are already only integrating with respect to the area, so I contains time, so we're not integrating over t, so we take it out of the integral, I omega squared over 2 pi, and you are left with ln of B over S, and then dA. Our dA here, we will assume that J and dA are in the same direction in this case. So in this case, it's along the z hat direction, but it's actually oscillating. So it's positive z hat at at half the time, negative z hat half the time. Then you will expect that the area, of course, the area is also oscillating in this case because the current is oscillating, so the area vector is also oscillating with the displacement current density. So J dot dA is just J times dA, or dA is also in the z hat direction. So you will get S ds d phi. This is the area, S ds d phi. So d phi is from 0 to 2 pi. S is from, in this case, 0 to B. So from 0 to B. So our displacement current is defined from 0 to B. So we'll assume that the radius of this inner cylinder is just very, very small. It's very negligible. Okay, so from 0 to B. And phi is from 0 to 2 pi. So you search for integrals here, you search for integral formulas, but actually you can do integration by parts in this part here for the differential over S, and you will get a value of, so ID is equal to mu naught epsilon naught omega squared B squared over 4 I. So it is a fraction of the conduction current. the displacement current is a fraction of the conduction current. So actually, in this case, the displacement current and the conduction current are actually basically in the same direction along the z axis. But the displacement current travels in the gap here, in the region between the two conducting cylinders. So it's in the gap. So our assumption here is that it's hollow. There's no dielectric in between here. It's just vacuum. The displacement current basically travels in the gap, or in the vacuum in this case. So that is our result for A and B. So compare displacement current and the conduction current. So it's easier to compare. Just take the ratio of ID over I, and mu naught epsilon naught. You will mu naught epsilon naught. That's actually 1 over c squared, where c is the speed of light, 3 times 10 to the 8 meters per second. So mu naught epsilon naught is 1 over c squared. So you replace mu naught epsilon naught by 1 over c squared, and you will get this one, omega b over 2c squared. So that is their ratio for this specific example. You will notice that the ratio of the displacement current to the conduction current depends linearly or directly on omega squared. Omega is the angular frequency. So displacement current can actually be ignored if you have a slowly varying current. Meaning slowly varying means a low frequency variations in current. So if you have small omega, you have small ratio, so you can just neglect. If you have a small omega, you can just neglect your displacement current. But if you have a fast varying current, then that's the time that the displacement current can no longer be ignored or can no longer be negligible. So that we have actually introduced this phrase before in the previous chapter, I guess, or previous lesson, I guess, about an example with a slowly varying current. So in that case, we don't need to include displacement current if the current is varying at a very low frequency. Okay, and that is it. That is the end of this chapter, the chapter on basic electrodynamics. So as a recap, we have discussed about Ohm's law, the relationship between the potential difference in resistance and current in a circuit. We have discussed about Faraday's law, and then lastly we have corrected Maxwell's equation, Ampere's law, to generate the general Ampere's law, with now the additional concept of the displacement current. So that is it for this chapter. So I will see you again in the future lessons. Goodbye.